So hi everybody. So it's lecture 18. Which is the last lecture before the break. And yeah, I should clarify that homework, I guess 8 is due after the break. So there's no homework due during the break. But today we're going to start a new chapter. We're going to take a break from eigenvalues. We're going to come back to them after this chapter, where we're going to combine this chapter with what we learned about eigenvalues. And the chapter we're going to start is chapter 6, which I'm going to call geometry of Rn. So in the beginning of the course, I told you that, at the end of the course, you would have some understanding of what a 1,000-dimensional space means geometrically. And we're going to develop that in this chapter. And geometry means we're going to introduce some new concepts into linear algebra, namely the concepts of length, distance, and angle. And so far, this is quite different, right? So far, the only concept we've used actually ever to talk about vectors is addition and scalar multiplication. We've never asked, what is the distance between these two vectors or, anything like that. So what we're going to do now is introduce these new notions into linear algebra so we can talk about geometry. So, it's not super, okay, geometry is, we can all agree it's a subject which deals with these concepts, length, distance, and angle. But if you were to distill geometry down to its, at least Euclidean geometry down to its essential, axioms, there are really only two essential things that define everything about Euclidean geometry from which everything else follows. And these are the essential facts about geometry are that the distance between 2 points is a straight line. And the other fact, which is really gonna be definitive, is Pythagoras theorem. From these two facts, you can derive all of trigonometry. You can derive a bunch of, pretty much everything else we'll use that's called geometry. So let me begin by defining lengths and distances. And then we'll see that our definitions match, these notions that we're used to from geometry that we learned before. So first I'm going to define the length of a vector. So given a vector u with coordinates, let's say with entries u1 through un in Rn, I'm going to define its length as, which is called the norm. The norm of u is a real number, which is just the square root of the sum of the entries. Okay, so this is a straight generalization of the formula that you're used to in R2 and R3. And the basis is that this is what should happen if Pythagoras theorem were to make sense in these higher dimensions. We'll talk more about that later, but this is the definition of norm. And this corresponds to the notion of length of a vector. Okay, and this is always non-negative. And then the distance between two vectors in Rn is defined as the norm of the difference. Okay, so these are our notions of length and distance. Okay. So we also said something about angles. So let me define what angle is. So given two vectors, let's say U and W in Rn, or let's write down their coordinates. Well, okay. Their dot product is defined as U dot W, which is again defined algebraically as U1 W1 plus U2 W2 all the way up to U and Wn. And this dot product is also just just a number. So so this is a number in R. So we said previously you can't multiply vectors. You still can't multiply them to get another vector, but you can you can multiply two vectors in this sense to get a number. And the relation between these concepts is that the square of the norm is just U1 squared plus U2 squared all the way up to UN squared, which is just the dot product of a vector with itself. So dot product of a vector with itself is always non-negative. And we're going to use one more notation in this chapter, something we haven't seen before, which is a transpose. Okay, so if you have a matrix, if you have a vector U, then its transpose is, for the first time in the course, an n 1 by n matrix, which you can also think of as a row vector. And so in this notation, the dot product can be written as a product of U transpose W. Okay, so these are the basic notions from which everything we say about geometry will arise. Really, there's only one notion. It's the dot product, because as we saw, the norm is also just a special case of the dot product. So before I tell you why this, has a geometric meaning, let me just mention its familiar algebraic properties of the dot product. So well, they're what you would expect, right? So if you have U dot V plus W, then you have a distributive law. If you have U times a scalar times W, then again, you have this distributive law. And then the last one is that the order doesn't matter. That's kind of obvious. Okay, so these are not very deep. What's interesting is the geometric properties, so the geometric meaning. And the key fact here is if you have two vectors in Rn, so I'm going to draw a picture, you have some two vectors like this, U and W, then the lengths are the norms, but the dot product tells you the angle between these vectors in the following way. The dot product is the product of the norms times the cosine of the angle. Okay, so this algebraic thing encodes angles between vectors. So I won't prove this. This follows from the law of cosines, which is a fact in trigonometry that you might remember from high school. You can derive it from that using coordinate geometry. I won't prove it. Instead, I'll just show you an example just to make sure you understand the meaning. Let's say I have two vectors. So here's one vector 1, 0. And I have another vector W, which is 1, 1. These are in R2. So actually, yeah, okay. I mean, in this case, the picture is almost correct, right? So if I make the lengths of these the same, then this is an adequate picture of these vectors. And let's calculate now. So the dot product between these vectors is 1 times 0 plus 1 times 1, which is just 1. The norms of the vectors are, so norm of u is square root of 1 squared plus 0 squared, which is 1. The norm of w is square root of 1 squared plus 1 squared, which is square root 2. And so what this formula is telling us is that the cosine of the angle between them should be, the ratio should be 1 over square root 2. And this would imply that theta is pi over 4, which is indeed true, right? The angle, if you plot these, the angle between them is pi over 4. So the dot product encodes the angle between vectors. Okay. Any questions?
I have a quick question.
Yes.
Why it has to be dot product? Can we say cross product because it's two norms times sine of the angle?
No, so cross product is something that you may know if you took Math 53. Cross product is a completely different thing because the cross product of two vectors is another vector. So that really, this is not like cross product at all in the sense that the output of this is a number.
Oh, okay, I see. Okay, I remember that.
Yeah, good question. Any other? Okay. So the most important thing about the dot, the most important case of this, I mean, you can use this to measure angles, but there's one angle that's particularly important, and that's 90 degrees. And so we have a special word for that. Here's a definition. Two vectors, let's say u and w in Rn are orthogonal if the dot product is 0. And you know, and what does this mean in terms of angles? It means that the cosine of the angle between them is 0, which means that the angle is pi over 2, or plus or minus pi over 2. Okay, so the vectors are perpendicular. So this is just a synonym of the word perpendicular. This is the definition of being perpendicular in Rn. And you know, again, the key property of Euclidean geometry is Pythagoras theorem. So let's prove a theorem about this definition of being perpendicular, just to see that it lines up with our existing notion of perpendicular. The theorem is Pythagoras theorem. The theorem says if u and w in Rn are orthogonal, then the norm of the distance between them is equal to the sum of the norms of the individual vectors. So the picture associated with this is you have a vector u, you have a vector w, and then this vector is u minus w. So if there's any justice or if there's a reasonable notion of orthogonality, Pythagoras theorem should still work, right? So the theorem is that Pythagoras theorem still holds. Okay, so let's prove this. So remember, orthogonality is defined purely algebraically as u dot w is 0, right? So we have to prove this theorem only based on this algebra, and maybe based on these algebraic properties, right? So let's do that. Well, we just calculate, right? So u minus w dot u minus w. By the algebraic properties, you have the same distributive laws. You get u dot u minus 2u dot w plus w dot w, right? So I use these algebraic properties here to do this rearrangement. But then by orthogonality, you know that u dot w is 0. So this is indeed just norm of u squared plus norm of w squared. And this is equal to norm of u minus w squared. So that's the proof. It's like a one-line calculation. Just a sanity check that we're on the right track. So that's the definition of orthogonal vectors, dot product being 0. So somebody raised an interesting question. Is the 0 vector orthogonal to every vector? Well, let's check the definition, right? 0 dot any vector is just, 0 times v1 plus 0 times vn, which is 0. Oh, sorry, these are not, these are just numbers now, which is just 0. So yes, 0 is orthogonal to every vector. It's a very good point. Any other questions? So orthogonality is the most important case of angles between vectors. Okay, so that was the first part. I guess I should organize this into sections. So the first part is orthogonality and dot product. The second part is now going to be, I'm going to talk about orthogonal sets of vectors. So right now we talked about two vectors being orthogonal. A very important notion is when you have a whole set of orthogonal vectors. So orthogonal set, orthogonal sets. So here's the definition. A set of vectors, let's say u1 through uk in Rn, is an orthogonal set if any pair of these vectors is orthogonal. If ui dot uj equals 0 whenever I is not equal to j. Okay, so the picture is something like, you have some vectors that might have different lengths, but between them, they have 90-degree angles. But it's just an algebraic definition. Okay, so this is the definition of orthogonal set. And there's a sort of minor upgraded version of this that we sometimes use. So if additionally the norms of the vectors are equal to 1, so for every I going from 1 to k, then it is an orthonormal set. Okay, orthonormal is just orthogonal, but all the norms are also just 1. Okay, and by the way, this also has a small piece of additional terminology. A vector whose norm is equal to 1 is called a unit vector. These are not conceptually difficult. They're just tiny pieces of terminology. Okay, so that's an orthogonal set. So let's look at some examples. So our favorite set that we've been looking at for a while, E1, E2, E3, and R3. Well, what are the dot products, right? So E1 dot E2 is 1 0 0 dot 0 1 0, which is 0. And then similarly for the other ones, right? So you have to check all pairs, E2, E3, and E3, E1. And so this is orthogonal set. But now what about the norms? Well, these are also just equal to 1. So it's an orthonormal set. Okay, so it's already normalized. Okay, that's kind of the easiest example. Let's look at a maybe slightly more interesting example, still quite straightforward. Let's look at these three vectors in R3, 2, minus 1, 0, 1, 2, 1. U3 is minus 1, minus 2, 5. These are vectors in R3. And let's check their inner product, right? So U1 dot U2 is 2 minus 2 plus 0, which is 0. U2 dot U3 is minus 1 minus 4 plus 5, which is 0. And U3 dot U1 is minus 2 plus 2 plus 0, which is 0. So it is orthogonal. But if you look at the norms, let's say norm of U1, this is square root of 4 plus 1, which is square root 5, not equal to 1. So it's not orthonormal. But there's an easy way to, I mean, we'll use this later. There's not really a huge difference between orthogonal sets and orthonormal sets if all the vectors are not 0. Because you could easily convert this into an orthonormal set. How would you do that?
Divide by the magnitude or the
Just
norm.
divide by the magnitude, yeah. So can easily make orthonormal. Just consider U1 divided by the norm, U2 divided by the norm, and U3 divided by the norm. So this is something we'll be doing in the next lecture quite a bit. So you can just rescale to make everything a unit vector. So it's not a big deal. And you can do this in general. Well, if all the vectors are non-zero. Okay, so what's the point of an orthogonal set? Well, the first thing is it's actually related. I mean, okay, it's just sort of geometrically kind of a natural thing, but it's closely related to linear independence. So the first theorem we're going to prove is that if you have an orthogonal set of non-zero vectors, then they have to be linearly independent. So if U1 through UK in Rn is an orthogonal set of non-zero vectors, then these are linearly independent. So it's an if then. Okay. So orthogonality is stronger than linear independence. That's what this theorem is saying. So in particular, this theorem implies that these three vectors are linearly independent. That's kind of cool, right? Because previously you had to do row reduction to check if something was linearly independent. But if it happens to be orthogonal, then you can tell more easily. So let's see the proof of this theorem, which includes an important idea that appears repeatedly in the study of orthogonality and in chapter 6. So we need to show these are linearly independent, right? These k vectors. So what's the definition? Well, the definition is, suppose you have a linear combination C1 U1 plus C2. By now this should be second nature to you. So suppose you have a linear combination that's 0. What do we have to show? Come on, we want to show that
non-zero vectors.
That
No.
they're all 0.
That they're all 0. Yeah. So suppose this is true for some Right. So I've assumed these are non-zero and orthogonal. So we will show that these have to be zero. That's what it means to be linearly independent, right? Okay, so how will we do that? Just a second, my Zoom is acting a little weird. Yeah, okay. Well, let's take it step by step. I want to show U1 is zero, right? I want to show C1 is zero first. So here's a sort of cool trick. If you take that first equation and let's take the dot product of both sides with U1. Okay, so U1 dot this whole thing has to equal 0 dot U1 dot 0, right? Okay, but now I can distribute the dot product because remember that's one of the familiar algebraic properties here, right? The first algebraic property. So this becomes C1 U1 dot U1 plus C2 U1 dot U2 all the way up to CK U1 dot UK. So does anybody see anything interesting about this expression?
Since they're all defined to be orthogonal, they'll all just become zero except for the first one.
Exactly. So because they're orthogonal, this will be zero. All of these will be zero by orthogonality. And so what's the conclusion? Well, by the way, this dot product here is also zero. The conclusion is that C1 equals 0 divided by the norm of U1 squared, which equals 0. If you just rearrange it, right? Or I mean, okay, let me not skip the step. Let me just do it here. So C1 times U1 dot U1 equals 0, but this is not 0. So then this implies C1 equals 0. Okay, so this is the beauty of orthogonality. By intelligently taking a dot product of a linear combination with one of the vectors, you can kill all of the other vectors. So sometimes I mean, you can call this the isolation trick. You can isolate one of the coefficients by taking a dot product. So I just proved C1 is 0. How do I prove C2 is 0?
Do the same thing, but with U2.
Yeah. So repeat with U2, U3, up to UK to get that all of them have to be 0. And that's a proof. Okay, so orthogonality is stronger than linear independence. That's the sort of summary of this. Any questions about the proof? Okay, so the conceptual summary is orthogonality is stronger than linear independence. So orthogonality implies linearly independent. Is the converse true? So does linear independence imply orthogonality?
No.
No. Why not?
Couldn't we just have like one vector, which it would be linearly independent, but not orthogonal to anything?
Well, okay, one vector doesn't quite satisfy this, right? Because if you have one vector, that's always an orthogonal set. Because remember, this is saying whenever you have two different vectors, right? But
Okay.
okay, you can just look at any of the examples you've looked at so far. Let's take 1, 0 and 1, 1, right? These are linearly independent, but not orthogonal. Okay. So orthogonality really is strictly stronger notion than linear independence. And when it happens, it's very nice because you can check it kind of easily. Okay, so what's the point of orthogonal sets? Well, linear algebra with an orthogonal basis is much easier than with a general basis. Okay, so let me define an orthogonal basis. So a subset U1 through UK Rn is an orthogonal basis of a subspace W of Rn if two things happen. The first one is the same as before. The span of the vectors is equal to W. And the second one is an upgraded version of linear independence. It said these are an orthogonal set. Or, well, okay, are an orthogonal set and non-zero. Okay, so previously all bases were considered equal for us, right? But now we're saying, hey, there's a special kind of basis in which you upgrade linear independence to orthogonality. And within that, again, if additionally all the norms are 1, then it's called an orthonormal base. There's a special kind of basis. So any questions about the definition?
Isn't this just imply that the elementary basis?
Great point. Yeah. For example, the standard basis is an orthonormal basis. You're right. That's an example. That's the main example of an orthonormal basis. Because the norm, going back to this slide, they're orthogonal and it's an orthonormal set and it's a basis of Rn, right? Yeah. So now the upshot is it's much easier to find coefficients to find coordinates with respect to an orthonormal base or orthogonal orthonormal basis. So let's do an example. Let's actually look at the orthogonal set we already looked at earlier in the lecture. So this is well, it's an orthogonal non-zero set, so it's linearly independent, 3 linearly independent vectors in R3. That has to be a basis. And now let's look at some vector in R3. So here's a vector 1, 0, 1. And we want to find the coefficients. So we know that x is equal to some coefficients times these just because it's a basis, right? We want to find the coefficients. Something we've done many times now in this course, right? Now the usual method is row reduction. So could row reduce, but here's a much quicker method using orthogonality. The easier method is again to use the isolation trick from the proof, but now we can use it in a calculation, right? So we know that x is equal to C1 U1 plus C2 U2 plus C3 U3. We want to find the C1 C2 C1 C2 C3. So can anyone think of something I could do to isolate C1?
Could you do the dot product with U1?
Yeah, take
on
the
both
dot
sides?
product with U1. So take the dot product of both sides with U1. And again, you get these cancellations, right? You get C1 U1 dot U1 plus 0 plus 0. And that's because of orthogonality.
Because U1.
Because U1 dot U2 is 0 and U1 dot U3 is 0. Right? If I distribute the U1 inside, I get U1 dot U2 and U1 dot U3, which are 0. And so then what this implies is that this C1 is just equal to U1 dot X divided by U1 dot U1, which is a very easy calculation, right? So U1 dot X is 2 minus 1, 0 dot 1, 0, 1. U1 dot U1 is, well, just the norm of U1, but let me just write it out. The norm squared of U1, 1, it's like this. So in the numerator, you just get 2. And in the denominator, you just get, sorry, I've written, oops, U1 is not this, U1 is something else. I've written X for U1. U1 is 2 minus 1, 0. 2 over 5. So no row reduction. And similarly, C2 is U2 dot X over U2 dot U2, which is, I mean, okay, U2 is 1, 2, 1 dot 1, 0, 1. U2 dot U2 is going to be 1 squared plus 2 squared plus 1 squared. And this is going to be 2 over 6, which is 1/3. And C3 is U3 dot X over U3 dot U3, which I calculated earlier is 2 over 15. Okay, so you can do this without row reduction. Any questions about this example? Okay. Yeah, it's very concrete, right? Really, in some ways, a lot easier than the previous section. So what's the general theorem? The general theorem is if U1 through UK is an orthogonal basis of a subspace W in Rn, and Y is some vector in W, then you can express Y uniquely as a linear combination of these, and there's a formula. Then Y is equal to U1 dot Y over U1 dot U1 times U1 all the way up to UK dot y over uk dot uk over times uk. So this works in general. And what's the geometric meaning? Well, I mean, the geometric meaning is, let's say you have some basis u1, u2, u3 of R3. And let's say you have some vector. Okay, that's not a color I was using before, so I won't use it now. Let's say you have some vector y. Then what this theorem is saying is that, well, you can express y as a linear combination of vectors that are parallel to these three orthogonal basis vectors. Right, so this is some C2, U2. Oh no, that's not U2, sorry, that's U1. C1, U1. And I guess this is C2, U2. And then this is C3, U3. Okay, so geometrically what you're doing is you're decomposing the vector into components that are parallel to these different. So this is parallel to U1. This is parallel to UK. Okay, so you're decomposing the vector into orthogonal components. Okay, so this is kind of like these high school problems, which you'll know what I mean when I draw a picture, right? When you've done this whole thing in high school. Okay, so that's what I want to say about orthogonal sets. Any questions about that? Okay, so now we get to maybe the most interesting part of the lecture, which is orthogonal projections, which is a very important operation that you can do with orthogonal sets. So to talk about this, I'm going to need to define a new operation on subspaces. So here's the definition. Okay, I'm not sure how that happened. It's actually kind of a nice color, but the definition is given a subspace W of Rn, its orthogonal complement is the following set, W perp. This is read W perp. This is a set of vectors in Rn such that set of vectors Z such that Z is orthogonal to every vector in W. Okay. So, I mean, okay, let me just make this concrete with a simple example. Let's say you have W is given as a span of E2 and E3, subspace of R3. So what does this look like? Well, we have R3. Let's plot it like this. So this is E1, this is E2, this is E3. Then W is the span of E2 and E3. So it's all this stuff here. Right? I mean, okay, and going into, right? But okay, I just want to emphasize that it's that plane. So what's W perp? Well, it's a set of all vectors in R3 such that that vector is orthogonal to every vector in W. Now, a vector in W looks like this, right? for all coefficients C2 and C3. That's just literally what span of E2 and E3 means. Okay, so that's infinitely many conditions. Can anybody see how to simplify that? What's written in the parentheses here?
Can we instead say that it needs to be E1 plus some scalar? Like it needs to be in the span of E1 and the span can be shifted horizontally or vertically?
So okay, you're getting ahead. The answer is that this is the span of E1, but remember vectors are always thought of as being originating at the origin, right? So we don't really think of shifting vectors
Okay.
in the course, but you're right. You're right that the answer is the span of E1, but the way to see that is this expression, you know, this is just equal to C2 Z dot E2 plus C3 Z dot E3, right? By the properties of dot products. So that means that actually, if just those two dot products are 0, that's equivalent to all of these dot products being 0. This is a set of Z and R3 such that just Z dot E2 is 0 and Z dot E3 is 0. Because if those are 0, then all linear combinations will also be 0, right? Just by linearity. Okay. And now, okay, you know, we have a way of computing this. Well, I mean, you can just, okay, what's a vector that's orthogonal to E2 and E3? There's actually only one vector like that. That's a span of E1. So the orthogonal complement here is just the span of E1. Okay. So that's the orthogonal complement. And now here's a fact which you can prove, although we'll see a proof of it in the next lecture anyway. This is always a subspace. We'll talk more about this in the next lecture. Actually, it's a nice homework exercise to check why this is the case. So this is a way of, given a subspace, how do you get another subspace? And that is the orthogonal complement that has a property that everything in the complement is perpendicular to everything in W. That's the definition, right? Anything in W perp is perpendicular to anything in W. So any questions about this?
So, Professor, is that the same thing as saying when we said W perp is the span of E1? Is that the same as saying like E1 is the normal vector to the space W?
Right. So we haven't defined normal vector.
Okay.
If you're talking about Math 53, then yeah, it is the unit normal. Yeah.
Professor,
Yep.
would there be any cases where W perp doesn't exist, like if all the dimensions are used up or something?
Oh yeah, so that's a great question. So the question is, what if W is just equal to Rn, right? Then W perp is a set of all Z such that Z dot, I guess Y equals 0 for every Y in Rn, right? So is there any vector that's orthogonal to every vector in Rn?
I mean, this is
Zero
kind of
vector?
The 0 vector, yeah. So the answer is it's a 0 vector. It's not empty. It's just equal to the 0 vector. Does that answer the question?
Yeah, thank you.
Yep. Okay, so that's orthogonal complement. And now we're going to ask an interesting question, which is going to lead to the notion of orthogonal projection. Here's an interesting type of question. Given a subspace of Rn and a vector y in Rn, which is not necessarily in the subspace, could be anywhere. Which vector, let's call it y hat in W, is closest to y? Okay, so concretely, what do I mean? I mean, I want to find some y hat which is in W such that this distance y minus y hat is minimum, is less than y minus W for every other vector in W. So let me draw a picture. This might become a little clearer if I draw a picture. The picture is there's a subspace W. This is a picture in R3. And to make it interesting, the subspace is not everything. It has an orthogonal complement, W perp. So let's illustrate W perp like this. And now we're given a vector. Maybe I should make this a little bigger, actually. Oh, sorry. So this is W, and there's W perp. That's the origin, and then there's some vector Y that's not in the subspace W. And what we're asking is, we want to find a Y hat in here, which is as close as possible to Y. So that's the question. Does the question make sense? Any questions about the question? So, okay, I mean, just for concreteness, let me write down a concrete instance of this question on the next slide. For example, I have W is the span of these two vectors, 1, minus 1, 0, and half, half, minus 1, which lives in R3, two-dimensional subspace of R3. And I'm given some Y, which is, let's just say 1, 0, 0. And I want to find Y hat in the subspace minimizing Y minus Y hat. These type of problems come up all the time. But let's look at the abstract question. For now, we'll get to the concrete one in a moment. So, so how do you solve this question? So, I mean, you're used to maybe doing this in 2D, right? If I give you a line and I give you a point, so let's do it up here. If I give you a line and I give you a point, how do you find the closest point on the line to that point?
You project it onto W?
Okay, but we haven't defined what that is yet. Just in 2 dimensions, right? If I give you a point and a line, what's the closest point on that line to that to the point?
The one that's like on the line perpendicular.
Yeah, you drop a perpendicular, right? So this is something you may have done in high school. And the point is the same thing works in Rn. So this is the beauty of geometry in Rn. A lot of the same things that work in 2D just keep working. So what's the key observation? Key observation is that if you have a point Y hat such that when you connect it to Y, you get something that's perpendicular to W. Okay, so what does that mean? That means if you connect this to the origin, this angle is 90 degrees. And actually this Y minus Y hat is perpendicular to everything in W. Then that has to be optimal. So if Y minus Y hat is in W perp, So this is the generalization of dropping a perpendicular. Then y hat is a minimizer. Okay, now what's the proof of that? The proof is actually proof is not difficult. Okay, that's too many boxes, but okay. But before I do that, is the statement clear? So, I mean, this vector, this difference, which is illustrated in the picture, if that is in W perp, then it has to be the minimizer.
So is sorry, is y hat a vector?
Y hat is a vector. Yeah. We're looking for a vector y hat in the subspace, right? So I gave you a y that's not necessarily in the subspace. And I want to find a y hat in the subspace that's as close as possible.
Okay.
Okay, what's the proof of the observation? Well, assume this is the case, right? So assume y minus y hat is in W perp. And now assume you have some other point W that's in W. So I'm just going to draw that here. And what I have to show is that y hat is closer to y than W is, right? That's what it means to be the minimizer. So just assume this is any vector in W. Now the key thing to notice is, so y hat is in W, right? So y hat is in W. Y hat is in W. W, this little w is also in W. So this difference vector, y hat minus W, that's also in W. Okay. But now, by the assumption, that means that this angle has to be 90 degrees, right? Because y minus y hat is in W perp. So y minus y hat dot y hat minus W is equal to 0. Okay. But now I can complete this triangle and apply Pythagoras theorem. So by Pythagoras, norm of W minus y squared is equal to norm of the other two sides, right? So what are the other two sides of that right triangle? So this is the hypotenuse. What are the other two sides?
The W to Y vector, Y hat vector.
Yep. So this is equal to y hat minus W norm squared plus, and what's the other side?
The W to Y vector.
Oh, we already did that, right? The
Oh.
hypotenuse is W to Y.
Y minus y hat.
Y minus y hat squared. Okay, but now I'm done, right? Because this is greater than or equal to y minus y hat squared. That's it. I just showed that y hat is closer than any other point in the subspace to y. So the key is to notice this orthogonality and apply Pythagoras. Pythagoras is a very useful thing, obviously. So any questions about that proof? It's the same as you're used to in 2 dimensions. The summary is that orthogonality which is this new concept, is equivalent to optimality, which means being the closest vector, right? Okay, so let's now do an example. Okay, somebody asked, how do you get the final inequality? Well, you get the final inequality because this norm squared, these are all non-negative numbers, right? So if you throw one away, you only get something that's smaller. Does that answer the question? Yeah. Any more questions about this slide? Okay, let's do an example. Let's solve this, right? So according to the observation, this y, I can solve this problem by finding a y hat so that y minus y hat is in W perp, right? So actually, let me explain the general method and then show you on the example. So to calculate y perp, y hat, sorry. We know two things, right? So we know y minus y hat. Okay. Or, let me just do the example first, actually. Okay, so what's the example? So W is given as a span of these two vectors, U1 and U2, right? And so we want to find this y hat. So we know two things. We know that y hat is a linear combination of these basis vectors. Why do we know that?
Because y hat is within W and W is just the span of those two vectors.
Yeah. And the other thing we know is that y hat, or y minus y hat, I guess I called it, is in W perp from the previous slide. Okay. So let's just write out what this means. This means in particular that U1 dot y minus y hat is what?
Zero.
0. And U2 dot y minus y hat is 0. Okay, but those are very useful equations, right? Because if I now plug in this equation, the first equation, into these equations, what do I get? Well, I get that C1, which I know is equal to U1 dot y hat over U1 dot U1. This is just from the previous projection formula, right? This is from this general theorem we already did, right? I know the coefficients, right? We know that this must be equal to U1 dot y. Right? Because U1 dot y minus, because U1, U1 dot y is equal to U1 dot y hat. And the second coefficient, which is equal to U2 dot y hat over U2 dot U2, must be equal to u2 dot y over u2 dot u2. Okay, so I use these two equations. These equations say that u1 dot y is equal to u1 dot y hat, and u2 dot y is equal to u2 dot y hat. And now I just calculate it, right? C1 is equal to, okay, so u1, so 1 minus 1, 0 dot y. The point is I know what y is, right? 1, 0, 0. u1 dot u1 is just going to be 2. So this is equal to a half. C2 is equal to u2 dot y. So half minus 1 dot 1, 0, 0. And now here you're going to get a quarter plus 1. So you're going to get 3 halves. And that's 1/2 over 3 halves. That's 1/3. And so the conclusion is that you figure out what y hat is. Y hat is equal to a half u1 plus a third u2, which if you do the arithmetic is this vector, 2/3 minus 1/3 minus 1/3. Okay. So actually, we really just used, in some sense, the way the proof worked is because of this orthogonality implies optimality or equivalent to optimality condition. We turned this optimization problem into these equations, which just say that u1 dot y is equal to u1 dot y hat. And then we just get formulas for the coefficients of y hat with respect to the orthonormal basis. So any questions about this example? So let me state the general theorem. Or it's actually a definition. Given a subspace with an orthogonal basis, let's say u1 through uk, and a vector y in Rn, the projection, the orthogonal projection, so this is the subject of this section of the lecture, of y onto w is defined as follows. It's denoted proj sub w of y. It's just the vector y hat in the previous thing. And it is exactly this formula. It's the linear combination of the basis vectors where the coefficients are these numbers. So u1 dot y over u1 dot u1 times u1 plus all the way up to uk dot y uk dot uk times uk. So that's the orthogonal projection. And this has two properties. So this has two important properties. The first is the best approximation property. And And that is what we just discussed, right? That this y hat is the closest vector to y, right? We just showed that. We observed that if you have this orthogonality condition, then you have to be the closest vector. And then we just checked that the vector, the projection, namely the vector with these coefficients, always has that property. So best approximation property is that y minus y hat is less than y minus w for every vector in W. So that's the closest vector in W, the subspace W, to Y. Any questions about that property? Okay. The second property is called the unique decomposition property. And that says, I mean, okay, I should draw a picture. All these things are related to, here, let me maybe shrink this. So let me draw a picture here. So the picture is that there's, there's a subspace W, there's a subspace W perp, there's a vector Y. The projection is this vector Y hat that lives down here. Projection onto W of Y. And that's the closest vector. Now the second property is the unique decomposition property, which says that there is a unique way to write Y as some Y hat plus Z with Y hat in W and Z in W perp. And it's given by the projection. It's given by Y hat is the projection onto W of Y, and Z. So Z is just what's left. Actually, Z is just this vector. Z is just Y minus Y hat. So this is in W, and this is in W perp. So these are the two key properties of orthogonal projection. It solves an optimization problem. It finds you the closest vector in the subspace to some given vector. And then it also decomposes the vector. It writes it as a sum of two vectors, one in the subspace and one in the orthogonal complement of the subspace. Okay, so the Z is in W perp. So any questions about this statement? Okay, both these perspectives are important. We're saying that this operation solves two problems at once. It solves an approximation problem and a decomposition problem. Okay, there's one important remark. The remark is that this formula written over here seems to depend on the basis, right? It depends on U1 through UK. It clearly uses U1 through UK. The remark is that the projection, actually the value of the projection doesn't change if you change the basis. So this projection, the vector itself, okay. Now, I mean, okay, we'll see a proof of this next time, but it kind of follows from how we derived the projection. The projection is just giving you the closest vector, right? And there's only one closest vector. So it has to be unique. The star is just a formula for computing it given a basis, but the actual vector itself actually is unique. It doesn't depend on the choice of basis. Okay, so the formula star depends on the choice of basis, but the vector itself doesn't. So just to sort of drive this home, in the example that I showed you here, what this is saying, so there's a decomposition and an approximation. So the approximation says that, well, the distance of y to the subspace is given by the difference between this, the norm of the difference between this y hat and y. So that's a norm of the vector. If you compute it, this is 1, 0, 0 minus 2/3. Okay, let me erase this. Minus 2/3 minus 1/3 minus 1/3, which is okay. So the first entry will be 1/3 squared plus 1/3 squared plus 1/3 squared square root. So that is square root of 1/3. So this is the distance of y to the subspace W. That's what the best approximation property is saying. That when you compute this projection y hat, that's the closest point. And the decomposition property is just saying y minus y hat is in W perp. We already knew that. Okay, so that's all I want to say about chapter 6. Have a great break. And yeah, see you after the break.
Thank you.
Yep, thanks. Any other question?
Thank you, Professor.
Thank you.
Yeah, I have a question on previous slides,
Yes.
like where you previously explained about best approximate. Yeah, how do you get the vector 2/3 minus 1/3 minus 1/3?
Oh, well, I took this linear combination of U1 and U2. I skipped the arithmetic. So U1 is a fixed vector, right? 1 minus 1, 0. And
Yeah.
U2 is half minus 1. If you literally take that linear combination, you get that vector. I skipped that step.
Oh, okay. And my second question would be where you said find 1, that we know 1. What does that mean by y equals C1 U1 plus C2 U2? Where do we derive that from?
Oh yeah. So we derived that because y hat is in W, right?
Yeah.
And U1, U2 is a basis of W. So y hat has to be some linear combination of these vectors, right? So this is since y hat is in W, which is the span of these vectors.
Oh, okay. Yeah. Thank you.
Right? Yeah. Any other question?
I just had one out of kind of curiosity. So most of the things that like we did at the beginning of the course when we were just talking about Rn, we ended up applying to like general vector spaces. Are we going to be able to do that for this, or is this just in Rn?
Yeah, you can do this to general vector spaces. We're going to cover that at the very end of the course. It's called inner product spaces. Yeah, there is a generalization of this to other vector spaces.
Okay, cool. Thank you.